Hello students, so in this lecture we would be discussing some aspects of light sensors. Now we will be discussing three different types of light sensing devices that are related to light sensing. The first one is called a photoresistor. The next one is called a solar cell, and the third one is called a phototransistor. Now let's start first with photoresistor. Photoresistor, as the name suggests, is a device where there is a change in resistance or with light, and it is mainly found in materials which are semiconductor materials which are sensitive to light, and one of the examples is being cadmium sulfide. And coming to the properties in cadmium sulfide, say for example, when there is no light, or when we say that the system is in dark state without any light, then the resistance is greater than 0.5 mega ohms. However, when 1 foot candle of light is present, the resistance reduces to about 1700 ohms. That's a huge reduction from 0.5 mega ohms to 1700 ohms. And if intensity is increased to say 100 foot candles, the resistance further decreases to almost 100 ohms. So in fact, with application of light, the current is increasing and the resistance towards the flow of current is decreasing. Now this can be presented graphically in this fashion. So we have temperature plotted in the y-axis, and resistance plotted in the y-axis, and we have light intensity plotted in the x-axis. So light expressed as foot candles, and resistance expressed in ohms, say. So with light intensities starting from 0 to say 100 foot candles, the resistance actually takes a curve like this, where at this point it is 600 kilo ohms, whereas at this point, say when it corresponds to 10 foot candles, it's 1700 ohms as mentioned previously, and it further reduces down to 100 ohms when the intensity reaches 100 foot candles. And so this region can be considered to be the dark region, whereas this region where there is no light, and this region is considered to be the region corresponding to light. This is how the plot looks. Now this photoresistor has lots of applications, some circuit applications to be precise. Circuit applications, like it can be used to change resistance values, change R, then it can be used to provide a sensor with voltage output, so we get VO, voltage output, and the last one is current to a load, supply of current supply. So although these three things are related, but it can be considered to be three different applications of a phototransistor. So let's understand graphically what these three applications mean. So for the first case, where there is a change in resistance, put it as R change. The circuit is actually like this. You have a resistance here, and you have this photoresistor situated here, and then you have this one, and so this is your resistance. This is where the light intensity falls, is the photoresistor, and you have resistance Rx at this point. So this Rx is equal to, we take this one as RL, so this is R into RL divided by R plus RL. So you can see the intensity of light intensity, there is a change in RL value. RL changes, and with this change the total circuit will experience a change in resistance. So this corresponds to the first application of a phototransistor. The second application is called the voltage output. So we have a voltage source connected, this V, connected again to a photoresistor, which is experiences light. Then there is a resistance R here, let's put it as R1. Corresponding to that we have a load V0. So this V0 will be then equal to, and this is grounded here, so this V0 will then be equal to R1, which is this value, divided by R plus RL into I. There is current flowing through it. So this gives you a voltage value. So again, this RL, this is your RL. This RL value, it changes with the intensity of light, and so we have voltage, output voltage. Is the output voltage. And going to the third application, where of the phototransistor, where it is acts as a sensor, which is used to supply current to a load, supply current to a load. So the circuit will look like this. We have the V0 here, then we have this resistor here, which is experiencing light, and then this will again be have a certain amount of current. It's an ammeter current, and so it will be able to provide current. This is grounded, so this acts as a current source. So this is the three applications of phototransistor. So coming to the next device, that is a solar cell, which is also a light sensing device. Solar cell is basically a P injection. So the P injection, and if you consider one of its constructions, that if we have an N-type substrate, N-type substrate, and it is on top of it. We have a very thin P region. So and that P region is again consists of metal stripes. So metal stripes, which are interconnected. So this actually forms the anode part of the device. And this interconnection causes an increase in current. Causes an increase in current. And see, so this is how it looks. So this is a silicon wafer, and on which you have this metal stripes, and in this version, interconnected metal stripes, and this is basically it is a network of forms a network of narrow metal strips, metals of narrow metal strips, narrow metal strips on top of, and it is forms the anode, forms a connected anode, and you have this voltage formed here. Now, in another way of looking this is how this construction is: you take a p-type n semiconductor, and you place a very thin p-type layer. So this is your N, and this is your P, and this is your formation of the anode layers here, These are the anode. And the light shines between the narrow anode contacts. So the light shines between the narrow anode contacts. The p-type, very thin p-type, p region, very thin p region, which is nearly transparent. Nearly transparent. And this one is acting as the cathode. Now in a solar cell, the back of the silicon wafer, so like this is the silicon wafer, this is silicon wafer, and the back of it, the back of the silicon wafer is coated, is metal coated, and it leads to formation of a cathode. So if you look the current voltage characteristics, so look at the current voltage characteristics. So if you plot current, sorry for the noise, current which is in milliamperes, plot with the voltage in volts. So this is 300 milliamperes. So this is how the plot usually looks like. So this is the place where the cell rating is 0.5 volts. So 0.5 volts at 300 milliamperes of current. Now light shining on the surface of the solar cell, it generates a voltage of usually of about 0.55 volts. This has been the average volts. Average volts, and under load the average voltage is about 0.5 volts. Now the solar cells again can be applied in circuits. Solar cells, they can be applied in circuits. by paralleling the cells for increased current output. By paralleling the cells for increased current output for increased current output by connecting the cells in series. Then we contain series. So if this is how the solar cell is placed, so this is one solar cell. This is how the solar cell, and this is again one more solar cell. So these are connected in series, and this is again connected in parallel to one more series. So this is one more series of solar cells. One more series of solar cells. So this is one series 1 solar cell connected in series, and this is series 2, and they are again connected to each other in parallel. So we get a high voltage here, around say 2 volts can be obtained. So the individual we have this individual 2 into 4 centimeter solar cells are available to provide a current of 300 milliamperes at 0.55 volts, or they can be also enclosed in modules so that they can provide voltage of about 6 volts at 50 milliamperes if they are in modules. So this is one more application. Another application of solar cell, a very common application, is in something called motor homes. Motor homes means car homes, or a car where moving home, whatever you can call it. So basically it's a car, and inside the car you are keeping all the you are keeping your home inside the car. So how the car looks. So here at the top, the rooftop, a solar panel is placed, so that there is a solar panel at the roof. And this is again connected with the battery here. Connected with the battery here. This what is called here is called a trickled charge. T-R-I-C-K-L-E-D, trickled charge. Trickled charging takes place. In this case, this is minus, this is plus, this is minus B, this is plus B. So the charging takes place in motorhomes when it is parked. First condition is it should be parked and under the sunlight. One should be exposed to sunlight. The sunlight will generate a voltage. The sunlight generates voltage through the solar cell to supply the trickle current. Supply the trickle current. This trickle current is actually helps to keep the batteries from discharging. This trickle current, it keeps the batteries from getting discharged. By getting discharged. And we do have a diode we have a diode which prevents reverse current. Prevents reverse current. Prevents reverse current when the battery voltage is higher than solar panel output. When the battery voltage is higher than solar panel output. So the many units are available with power ratings from 2 to 50 watts because of motorhomes. Now coming to the last device, that is number 3, that is a photo transistor. Now, phototransistor, as in the case of, let's try to understand what is a transistor is, how it works, then we will come into the phototransistor. The transistor can be an NPN type or a PNP type. So an NPN transistor, it looks something like this, the symbol, the arrow going outside. So you have the base here, it's the base. This is the collector C, and this is the emitter E. So this is the collector current IC, and this is the emitter current, and this is the base current IB. So IE is actually, emitter current is a combination of the collector current and the base current, and there is a transistor current gain, a quantity called transistor current gain, HFE, which is actually the amount of collector current obtained with respect to the amount of base current that is being provided. And so we can write IC is equal to HFE IB, and it is known as the transistor current gain. Transistor current gain. So similarly, as we have an NPN transistor, we do have a PNP transistor also. So if we compare both two transistors, a PNP transistor will look a little different. We will have the arrow pointed in the opposite direction. This is the collector, this is the base, and this is how the IB current is going, and this is the emitter E. Now, so the base current is important here. So this HFE, which is the transistor current, it is basically the amount of collector current received with respect to the base current. Now, in the case of a photo transistor, whether it is an NPN or a PNP, the role of the base is taken by light. So we don't have a base, we have a light, and that light creates a current which actually makes the transistor, causes the collector current. Okay. And it usually works in, it is sensitive to IR light, infrared light. So this transistor again, this photo transistor again, has got some applications, like it is used, so photo transistor, again can be used as logic output, linear or logical output. Linear and logical output means, suppose you have photo transistors connected here, so it has no base, however it is sensitive to light, so it is creating some sort of current. Now the current diagram says that you have resistance here, and then we have another resistance here, which is called an adjustable resistance. Adjustable resistance here, and this is again connected to a proper driver transistor. So this transistor again will, or the current produced by this transistor this phototransistor is being coupled to the base of the driver transistor. So here the photo transistor, that means this one is being coupled to the base of the driver transistor. So now if you look in the current versus diagram, so of a phototransistor, so we plot milliamperes, the current here in the y-axis, and the voltage, or let's say voltage of collector emitter voltage, VCE voltage, and one can find plots like this. However, the intensity of the light will increase, so we'll also plot something called a resistance load line here. So this is the dotted line is the resistance load line, and the intensity, the more light intensity produces more collector current. So it is more light intensity which is being measured in terms of foot candela. It implies that there is more collected current. Now you can also make a relay driven circuit through a phototransistor. These we can switch off and switch on a device, so relay driven transistor. So again you have the phototransistor placed here, which is sensitive to light, so it is generating some sort of current, and to it we have this adjustable resistance, again adjustable resistance, and this is again connected to another transistor coupled with the base, and again this is the emitter, so it looks, that is the collector C. So it is a relay contacts, so it produces either contact as NO, NC or C. NO contact or NC contact or only C contact. These are the different relay contacts. Basically it gives you an on and off situation based upon what kind of current is being fetched, is being generated, and that is again depending upon the intensity of light that is falling on the phototransistor. So let us summarize what we have studied in this last summary. We have discussed some of the light transistors and IGHT, light sensitive devices, let's call as light sensors. So the first one is the photo resistor, where the resistance changes with application of light. Second one is the solar cell, which is basically a PN junction, and which works with the application of light. And thirdly, we have discussed about photo transistors, where the action of the base, or the base gets replaced by light, and it is used in different devices. Like the most common of application of solar cell is in batteries and in motor homes. uh, this is again in relay and in logical outputs. And this photoresistor again has got applications in creating voltage, providing current based upon the light, current source, etc. That's